Dear participants, welcome back for the second session. So I hope the first session was very useful for all the participants. As I had to leave because of some official meetings, so I could not attend the full session. So I think we can wait for 2 more minutes, as I am seeing that only 5 participants have joined out of 11. So let's wait for 2 more minutes, and then we'll start. Indrajit, is it okay?
Yeah, sure, sir.
Devendraji, I think we can start. As 9 participants have joined. So, I welcome you again for the second session. So we will be continuing with the discussion related to basic electronics in this session. So over to Devendra sir, please.
Okay, sir. Let me just share my screen now. Okay, so hope you all can see my screen now. Okay, so is it visible now?
Yes, sir, visible.
Okay, okay. So now in last session we saw about what this tool is, and we tried one small experiment of Ohm's law. That also I have the data here. Okay, so similarly, you can take multiple readings and plot, and your students can do the same things at their end, and send you the final results. You can give them the values of the circuit that has to be used, and accordingly, they will share the results with you. Okay, so let me just delete this chart. Okay, so now. Okay, so in this session, we will be looking at diodes and how we can make some basic rectifier circuits using diode. Okay, so let me. Okay, we left Kirchhoff law also in between. Okay, so Ohm's law we have done, and then Kirchhoff law also we'll look at. Like it is again very basic, simple thing. Like first law is KCL, which basically states at a particular junction the current value coming inwards sums up to the current value going outward. Okay, and the KVL states that if you basically measure the voltage across in a closed loop, it should be equal to 0. Okay, so it sums up to 0. So these two things we will again quickly look at. and then we will move towards our comment sessions. Okay, so let me just make a basic circuit first. Okay, so change the orientation of any of these component. You can use this particular button. Once you select it, these four things come up. This one is to copy it. Like you can see, I can copy it now here. Okay, then this one is to reverse flip it. Okay, which anyway in case of resistor doesn't matter. This one is to delete it. Then this one is to rotate it. Okay, so I will just put it like this. Let me just make a simple circuit here. Okay, I will now put one DC voltage. Okay, so let me just copy this one also. Okay, so this is the same junction we are using. Okay, so now let me just connect it here. Okay, then these two will come here. Okay, so the voltage I will give, let's say 50 volts. This I will give, let's say 4.15 kV. This let me just remain 1K. Then this could be, let's say 700 ohms. Then this let me make 900 ohms. Okay, so we have multiple resistance here, and this is the junction we will be talking about. And on this junction, you can see that this is the input current line, and this, then this, and this would be the output. So whatever current is coming here and would be equal to the sum of all these threes. Okay, so let me just put some current probes like here. Okay, so we will see what current is coming here. Then one we will put here, what coming current is going here. Then one we will put here. Then another we will put, let's say, here. Okay, so now we have current of all the values. Okay, so now let me just run it. Oh, so no ground is connected. So let me just stop and connect the ground here. Okay, so now if I run it, so now you see 11.28 milliamps, and these are the three different uh, junctions currents. So let me just open up the calculator. So let us just calculate the outward current. We have three outward currents, like 4.5526 plus 3.5409, which is this one and this one. Now the third one is this 3.18, 3.1868, which is equals to 11.280, which is this one. So the input current is equals to the sum of output currents, outward currents. Okay, so this proves our KCL, a simple basic circuit. Now you can just give them the different values and ask them to calculate all these things. Okay, so same here we can try to look at Let me just modify the circuit a little. Okay, and then KCL also we can look at here itself. Okay, so this is okay. So this is our circuit. Okay, then we will just make it, let's say, a little less, 8.5 volts. Okay, now I will apply some voltage probes like here, which will measure the voltage at this point and the ground, which is basically equal to this particular voltage. Okay, now I have to measure voltage between this, across this and this. So this complete thing would, the voltage drop across this complete loop should be equal to 0. Okay, so let me put some other probes also, like one here and one here. Okay, so now these probes will also measure voltage between this point and the ground, which I don't want. So I want to measure voltage between this point and this point. Okay, so again I will put a reference point here, which is reference 1 and the reference 2. Okay, now this particular probe will measure between reference 1 and this point, and this one will measure between this point and reference 2. Okay, so let me just run it once. So you can see 8.5, then this is minus 6.8495 and minus 1.6505. So let us just sum it up once. So minus of 6.8495 minus 1.6505, which is minus 8.5, which is what this is. So 8 minus 8.5 minus 8.50. So again, the KCL also holds here, and both the basic laws are working. Okay, so this proves our KCL and KVL. If you have any doubt, let me know. Otherwise, we'll move forward.
So is it possible to enter the value directly, or we have to move only the slider?
What, sir?
Suppose I want to put the results value as a 4.123.
Okay, here. Okay,
So I
so
like
you
that.
can click here.
Oh, you can. Oh, it is possible to enter also.
Yeah, 1, 2, 3, 4, 5, whatever you want.
Oh, okay.
So you can slide also, or
It's
you can
possible to enter
directly
also.
write here also. So to write, same goes voltage also here. Okay, you can just click here and particular voltage, that is up to you. And let's say if you want it to be like mega, you can either do this, or you can just simply 1 and capital M, which is equivalent to 1 mega, or 1 capital G, which is giga, and 1 capital K, which is kilo. So that way you can work.
Okay, sir. Yes, sir. Thank you, sir.
Okay, so any further doubts? Okay, so we'll move forward with our diodes and rectifiers. Okay, so let me just delete this. Okay, so now we will look at our diode circuits. So KVL and KCL we have done.
So I have doubt, sir. I have one doubt.
Yeah, tell me.
Since you want to copy this entire circuit, is it possible to copy and paste it in somewhere? So I want to draw this instead of drawing circuit. Is it possible to copy and paste it in a web file?
Okay, let me tell you. So like if you go under circuits here, so you have your circuit, then your public circuit. Let's say I go to a public circuit. Okay, so we have all this sort of circuit that people have made here. Okay, I can just copy one of these. Okay, so let me just look at one. Kirchhoff voltage law. If I search this, someone might have already done this, like this you can see here. This person has done, so I will just open this thing. Okay, so this is a circuit, and I can run and I can see all the way whatever data they have data is coming. Okay, and I can export it, the schematic image, like I can save it here, the image you can see the circuit image. Similarly, graphs and data and everything you can put. Then you can save this also in your circuits, the same thing. Okay, so let me just my circuits. So you see, we have the Kirchhoff's law here. So I went there, I saved it, and it is showing under my circuit.
Okay.
So I can delete it, I can open it, I can edit the details. Okay, so but what you are saying, like I can, if I can copy paste, that cannot be done. Like let me just show you how. What you're saying, like if I control A and control C here, okay, then
That's what I'm asking.
yeah. So if I go here and control V here, there's nothing. I cannot paste it. So I can save this particular thing as it is. I cannot copy paste.
Oh, okay.
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 Okay. So I hope that is clear. Let me just delete.
Okay.
Sir, can you please repeat it, sir?
Ma'am, what he was asking that if let's say I have made a circuit, and normally in Word file, and what we do, like we press Control A to select and then Control C to copy, and then
Where
what we
will
do,
we
we
get that at other circuits, sir? How will we search for other circuits?
okay, that part you are saying. Okay, so you have to go to your home page like this. Okay, then under circuits, you see public circuits. Public circuit, people have done made a lot of circuits here for you, which you can easily monitor. Like you can see on a single page, you have like 20 circuits, and you have such this many people. So there are
Sir, we cannot hear you.
Is it audible, ma'am?
You are audible, sir. You are
Yes,
audible.
sir. Audible.
Okay, so you can search for these circuits. Like I want to particularly search for let's say full wave rectifier. I will just go under the search menu and I will just click search, type my tag and search it. Now you see full wave rectifier, multiple circuits have come up, which people have designed. I can just use any of them and work on it. Okay. So like this one I can see. If I want to copy, I will just click copy, and you see it is processing here. That means it has been copied to my circuits also. So let me just go back. Uh, this card. Okay, so if I go to my circuits now, you see I have this copy of full wave rectifier also, which is the one I just copied. So I can copy other circuits like this. I cannot copy like control A and control V. That won't work here. Okay, so that way we are restricted here, which actually should be a bit easy. I guess it should be a good thing because students cannot copy that directly. Okay, so I'll just again go back now. Uh, okay, so should I move forward, or any further doubts are there?
No, sir. Please go ahead, sir.
Okay, sure. Okay, so now we will move towards our uh, diodes. Okay, so we'll see how a diode works, then what all we can do with diodes, like rectifier circuits and everything. Okay, Okay, so in the end, I will ask you to make one half wave rectifier also on your own. We'll spare 10 minutes for that particular exercise. And till then, I will show you all the different circuits that can be done today. Okay, so now we'll move forward with our rectifier circuit. So this we have done.
I think recording is, sir, I think recording is not on. If you want, I think it is. You can
Recording.
control the recordings.
No, recording is on, sir, I guess. Thali also, can you just please check? Okay, okay, thank you.
Okay.
Okay, so now we will look at the PN diodes, like diode IV characteristics, and this is how the characteristics would look like. Okay, so we know the breakdown voltage is this, the mean. So we will just check it in the forward bias. Okay, and then we'll try to plot it like we did in the normal IV characteristics. So let me just take a diode here. Okay, so this is a generic diode. Obviously, in this case, like a particular part number if we have. So we know that this part number is going to have this much breakdown voltage. But in this case, it is a generic one. So what I will do, I can just double click over it. This window will come up and I can give all these parameters here. Like you see, I can define all this parameter and I can make it a specific, what you can say, specific diode. Okay, so I am anyway just interested in the breakdown voltage, which let's say I will make 1.7 volts. Okay, so this is the breakdown voltage. Okay, so I have given that. So now I will apply one power supply here. Okay, and that would be my circuit only. Nothing else is required. Okay, so let me just connect it. Okay, then ground is here. Okay, now I have to measure the voltage drop across this particular diode and the current. Okay, so current anyway we know it's in series, so it won't change. So I can measure current anywhere, but voltage drop right now I have to measure between across this particular thing. Okay, so let me just give it a reference here. Okay, so double click here, give the setting that it has to measure voltage from this point to this point, between this. Okay, now just for my curiosity I will measure this voltage also, like the voltage of this particular uh, power supply. Okay, so if I start with, let's say, 0, let's say if I give 0.1 volt. Okay, so I will start with this and let me just run this. So you can see the current right now is too low. Okay, then we have voltage drop is 100 millivolt, or we can say 0.1 volt. Right now we'll just see first how it increases. So let me just slide it pretty slow, and as soon as we crosses 1.7 it should shoot up quickly. Okay, so it is linearly increasing right now. You can see the current value. Okay, linearly increasing. Okay, now you see it has increased a lot from here to ampere. Like you see, from here at this particular point it shooted like anything, like 50 ampere. So this is the knee that we were talking about. Okay, so let us just try to plot it. Okay, so we will plot it like on every one, every few readings. Okay, let me just open the sheet. Okay, so voltage. So we will start with 0.1. 1 second. Okay, so and the voltage is sorry. The voltage current here is right now 567 femtoampere. Femto is 10 to the power minus 15. Okay, so 67 e to the power minus 15. So sorry, but we have to write it. Now we will put it on 0 0.2, 0 0.3, 0 0.4, 0.5, 0.6, 0.7, then 0.8, 0.9, and 1. So these are the readings that we will be taking. Okay, so now let me move to 200, and here we have pico, which should be equal to, I guess, minus 1. Okay, so 23 pico. Now let me just put it 23 e to the power. So now we will go for 0.3 volt and 0.3 volt. Let us see what it gives. It is nano, 1.09 nano. Nano is minus 10. 1.09 e to the power minus 9. Okay, then 0.4. Let us look at 0.4. So we have 52 nano here. Okay, so 52 e to the power minus 9. If I make it, let's say 500 millivolts, 0.5 volts, we have 2.48 micro, which is 10 to the power minus 6. What was it? 1 second. 2.48. 2.48 e to the power minus 6. Now we will move towards 0.6 volts. Okay, we have 118.8 micro. Okay, so 118.8 e to the power minus 6. If we make it 7.7 volt, we have 5.67 milli, which is minus 3. 5.67 e to the power minus 3. Okay. Now 0.9 we will do 7.8. 271 milli. 271 e to the power minus 3. Okay, so the next stop is 0.9. It's 12 ampere. 12 how much? 12.94. And for 1 ampere, 1 volt, it is 618.51. 618.51. But we have to plot. Now if I select this, go here and plot, you can see that it shooted up here. Okay, so this could be right around the 0.9 or 0.7 is what we can call it, the knee. Okay, we have one slide downwards here. Let me just see what it is. After 0.9. No, it should not have happened. Right. Anyway, that is okay. So this was a forward bias we were checking. Similarly, we can check for the reverse bias also. Okay. So this was like this is how you can ask your students to plot the IV characteristics. Okay, so simple circuit, a diode and a battery only. Then you put in your voltmeter and ammeter, and you can just try to work on it. Okay. So this is one thing. So if you have any doubts, let me know. Otherwise, we'll move forward. Okay.
So
Sir,
where to change the threshold value, sir?
What, ma'am?
Where to change that value first for the diode?
Okay.
1.7.
Uh, if I go here, you see under this advanced parameters, all these things are here, like transit time, zero bias junction capacitance. All these values are here. You can see
Where, sir?
forward diode depletion capacitance coefficient.
Can you see, show once more, sir? Advanced parameters.
Okay, you just go on the diode, double click over it. Okay, so this window will appear. Right now, let's see if I
Okay.
close it. Okay, and I just go to double click here. Okay, so this window will come up. I just have to click on the advanced parameters, and all these readings are here. See, all these readings are here. So these are standard parameters that one measure in any spice model, and accordingly the spice model works. So you can change all these parameters here and accordingly match it with any of the standard part number that you might have in your lab. So you can ask your students to put in values of, let's say, some particular diode, okay, which you generally use in your lab. So whatever value result they will get should match the real IV characteristics. Okay, so accordingly you can ask them to make it for, let's say, some X diode or Y diode. You can just give them multiple part number also, like this part number they have to use or this part number they have to use, and accordingly they can use and let you know the results. Okay. I guess that clear your doubt now.
Yes, sir. But after the diode, I am getting the voltage as 0 volt.
After what, ma'am?
After the diode, I placed a voltage, but it is showing the 0 volt.
Uh,
Current is measuring.
Ma'am, 0 volt it is showing because you might have not used it with the reference.
I have
Because
used
one,
that reference.
you have used the reference. No, it should not have. Like normally, what happens if you are measuring between this point and the ground, it will show you zero, and with your measuring not. Like here, it is showing -1 volt.
In my case, it is 0.
Uh, just a second, ma'am. Can you share your screen? I will check. Just share. I will check. One second, ma'am. Okay. Double click on this voltage PR2, probe number 2. You see here, the voltage reference is ground only now. The voltage reference is ground. You come at the right hand side, under functions, right hand side, man. At the right hand side, there's a table. Right hand side,
Yes,
not
sir.
left, ma'am. Not left. Right hand side, you see this table.
Yes, sir.
Yes, here you see this voltage reference here. Just come below. This, yeah, this. You have to select this as reference. Now, if you run it, now just run once.
Okay.
Now you see you don't have zero because
Okay,
you have
thank
to
you,
measure
sir.
between these. Okay, maybe you might have done with the other one. Okay, okay. So okay, we'll start back now. Any further doubts?
sir, can we plot forward and reverse bias characteristics in same graph?
Yeah, you can always. But you have to just add the readings. Like right now, we added these readings.
Yes,
Let's
sir.
say it started adding -1, -2, -3 reading also. It will show that also. So
So,
that can be done.
yes, sir. First and third quadrant in same graph.
Yeah, it can be done. Yeah.
Okay.
Yes. Let me just give you an idea how it can be done.
Yes.
You can measure it like that only, like minus 1, sorry, it's 1, minus 0. Minus 0.9, minus 0.8, minus 0.7, minus 0.6, minus 0.6, minus 0.5, minus 0.4, minus 0.3, minus 0.2, minus 0.1. Okay, so these are the readings. Let's say I'll just give some let me just give some formula. I will just negate these values and I'll put nothing else. Okay, so now if I just select this and I'll go here, so you can see now we have plotted all the 4 quadrants here that you can do.
Yes.
Okay,
Thank
so
you.
obviously the readings are wrong here in this case, but you can
Yes.
again give the readings and measure the current and accordingly place. So the complete forward and bias, forward and reverse bias, you can get the results. Okay.
Yes. Thank you, sir.
Okay. So if there are any further doubts, let me know. Otherwise, we'll move forward. So I will delete this. Okay. Now let us just move towards some rectifier circuits. Zener diode is also there, where we'll look at it later on. Okay, so first thing is half wave rectifier, and this is a basic circuit of any half wave rectifier transformer, which will take in the AC current and transfer the current voltage, and through this across this resistance, we will measure the half wave rectified output. Okay, we all know the working that in forward bias, it will when there's a positive peak, it will be in forward bias and it will work, and when there's a negative peak, it will be in reverse bias, and generally in reverse bias, as you see here, the breakdown voltage is bit large. Okay, so it won't break and it will just suppress that particular part and we will get a flat. Okay, then again forward peak will be transferred and negative peak will be deleted. So that is our half wave rectifier. So this is the basic circuit and I will just quickly demonstrate this to you. So first we need a transformer, which is one primary, one secondary. Okay, I will need one AC source. Okay, then I will need a basic diode. Okay, and I will need one resistance as in load. Okay, so let me just rotate it. Okay, so now, so let me just quickly connect my circuit. Okay, so now this is how I will connect. Okay. Okay, so the voltage that I'll give here is, let's say, some 8.3 volt, and frequency I will give it like 50, normal 50 hertz that we get. Or if you want, you can try like 220 also here. 220 volt AC, 50 hertz, which is what we get in our main supply at home. Okay, so now I will just connect this particular diode here. Okay, then the diode will go from here to here, and then from here I will come back here. Okay, and now I need to measure the original wave that we are getting here. Then I will have to measure the voltage across this resistance, which is our load resistance. And obviously I'll be using a reference because we have to use Like we have to measure across this, not across the ground and this point. So I will just go here, select reference 1. So it will measure now between this, okay, across this. Okay, so 220 volts, 50 hertz input we have given, and diode is there, and our load resistance is here, which is 1K. You can change the value. Let me just run it. Okay, so there is no ground. Let me just. I always forget the ground. Okay, so ground is connected here. Now if we run and if we split the screen, okay, you see we are getting some waves. Let me just as a normal oscilloscope, we have this time per division, and we can have this volt per division also. Let me just give it a trigger also. So, okay, so you see right now we are getting the negative because I'm measuring in opposite direction. Let me just pause it and correct it. Here. Then this video here. Okay, now let us try. Okay, so now if you see here, we are getting the voltage, okay, which is half wave rectified. Okay, so this is a half wave rectifier circuit, which has given us the positive peak. So if you want negative peak, you can reverse this diode. Okay, so let me just flip it. Okay, not flip it. Let me just delete these wires, and I will show you how you can get the negative peak also. Now I flip it and connect it in the same connections. So you see here we are getting the negative peaks. Okay, this is a basic half wave rectifier circuit. Okay, now if you want, you can export the graph data on a CSV file or the image. Okay, you can see I have downloaded, and it has sent this image. Let me just open this image. What is happening? Here is the image. Okay, so you can see this image has been downloaded, or I can also export the schematic image, which is my circuit diagram. Okay, 1 second. Done. So this is the circuit diagram we were using. Okay, so similarly, we can have the circuit and the waveform and the waveform data also. So we can have all these things. So you can ask your students to implement the circuit and share these parameters with you so that you can cross-check it. Okay, so this was our half-wave rectifier basic. Anyone having any doubt on this?
So what is actually the step down ratio of the transformer? You are giving a 220 volt. The output automatically it will reduce to low voltage.
Yeah, you can give a low voltage. So this is anyway just to show you how the system works. I don't need to even add a transformer in between. I can just directly give a supply here. Let me just show you that how that works. Okay, so if I take this, let me just connect it here, and this one will go here. This one will come here. Okay, so this voltage here. Okay, so now if I run it, and let me just show you here. You see, now we are getting the same thing with us. So I don't need a transformer, but in labs generally we ask students to put in a transformer also in between, na? Because we basically are working on 220 volts, and we use a step down to convert it into maybe a 9 or 30 volt AC. Then we use this circuit in forward to clip the negative wave and try to convert it into a DC. Okay, so anyway, I just showed it in that.
So how to see the waveform? Because it automatically come or we have to after
Not
simulating.
automatically. So we have added these probes, na. One probe is here and one probe is here.
Oh.
This one is the original waveform, the original between this point and the ground, which is our main input, 50 volt, 50 hertz sine wave, and this voltage is across this particular resistance, which is our load resistance. So that is why you see this blue one is clipped, and the green one is the full one. Green one is our this. You can see the color coding. This one is green, and the full wave is the green. Now this one is blue, and the clipped wave is blue. So blue is blue. This one. Okay, so color coding also you have here to just see which probe is which one. Okay.
Once
So
we
that-
run, the waveform will automatically come, or we have to go.
Yeah, automatically it will come. It will come automatically. You just so right now you will see the screen. If you have to see the waveform, you have to go to this graph, or if you want to see the both things, then you have to split. And you will see the both circuit and your waveform. Okay. So this was a basic half wave rectifier circuit. Any doubts?
Sir, can we edit the legend part in figure window, sir? The naming of two signals, PR1, V1, PR2, V2 minus, sir, on upper corner, sir.
So this you have to change here now.
Okay.
Here, like if you want to, let's say
Output waveform or something.
VO, V out.
V.
This one is let's say V in.
Right.
So you can give here, and now if you go on the graph, where is 1 second? Let us just run it. Okay, then if we go on the graph here, you see VO and V in, VO and V in.
Right.
That's what
Thank
we are.
you.
Okay, here you
Yes.
can see VO and V in. So these things you can always change.
Yes. Thank you, sir.
And also we have some other basic parameters like time per division. If you want to expand or compress on the time division, and then we have, if you want to, let's say, disable one particular channel, that also you can do. Okay, so by this you can deselect both or select one, and you can basically give this on falling edge or rising edge. Then trigger options are there like auto, single, normal, none. Okay, so these are the basic DSO functionality that we have here also. Okay, so
we can find efficiency, the ripple factor, and all the other parameters. How can
Ma'am,
we find that?
you can download this wave. Like these things we calculate on the readings, like what voltage we are getting and all. That way we basically calculate all these factors. So what I will do, I will just export this graph data on a CSV file, which is my Excel file. Okay. So once that happens, I will basically have all the data. Like this you see right now, this file is downloading. So based on this data, I can just have that calculation also. Okay. So once it is uploading. Okay, so you see these values you have got for X trace, then your Y, then this is the V1, V in, sorry, and your V out. So you have all the values with you. Okay. And obviously you have the timestamp also here. Okay, now you can just measure this value and calculate all the different parameters that you want. Okay, so
Manually we will have to calculate rest of the parameters.
Yeah, exactly, like in a normal lab we do na. That multisim live is just like our breadboard. So you will just connect your circuit there. You will note the readings in a notebook, and then on the notebook you will do all the calculations. So something similar is what we are trying to do, so that whatever wave students have followed in the lab up till now in their previous years, they will keep on following the same methodology, and they will implement the same things. So similarly, they will have the same methods. Okay.
Okay.
Hope that is clear, ma'am.
Thank you. Thank you.
Okay. So if there no doubt, I will move forward with our next circuit, which would be 1 second, which would be a full wave rectifier, and the circuit for that is this one. We basically put in two trans. We now in this case we basically use a transformer with a center tap also. Okay, and we put our load resistance here and two diodes here. This one will pass a forward bias, the positive peak. This one will pass a negative peak, and we will have a complete result. Okay, so let me just quickly make this for you. So we will need a transformer with center tap, which is this one. Okay, so now again I will put one supply voltage. Okay, and I will need two diode in this case now. One here, or I will copy this one only. Another here. Now I need a load resistance, which will be this here. Let's see. Okay, now let me just connect it. Okay, now connect this one. Okay, now this one will go here. Okay, and this one will go here. And this will come here and here. Okay, so this is what. Now I will add a ground first of all here. So let me just give, let's say, some 50 volt, let's say some 10 volt, okay, some 52 volts, and frequency, let me give just 50 hertz. Resistance is 1K. I'll keep it as it is. Now I will measure first this one. Yeah, okay. Then I will take another road and I will measure towards this. And obviously, I have to measure across this resistance. I will use the voltage reference. Double click on this, go on the settings here, and select reference 1. Okay. So now, if I run this program, let me just split the screen. Okay, 1 second, we are getting the wave, but it is, as you can see, is in the negative side because I have measured opposite in this case. So this and this. Okay. Now let us just run. Okay. So as you can see, like it is running right now. So let me just give it some trigger. Now you can see we have our full wave rectified. Okay. So this is one thing. This is another circuit, full wave and half wave rectifier. Okay. Any doubts in this? Are you having any doubts in this?
Sir, can we add a capacitor at the output?
Yeah, that is a separate circuit. We are
Okay.
just going with the flow. First, half wave,
Okay.
then bridge circuit would be there. Bridge circuit with your pi filter also. All these things we can try.
Right.
Okay, so this is one thing. I hope if there's no doubt, we'll try and we'll. Okay, so we will just make a bridge circuit now. Okay, like this was our full wave rectifier. Now we will go for full wave rectifier bridge type. Now this is the circuit, and let us just make this quickly. So I'll not use transformer in between, as I've shown you. The working is almost same. Let me just put 4 diodes. Okay, so 4 diodes are these. Let me just connect it now. Oh, sorry, not this one. Okay, so I will connect these. Okay, and here this one will go here. Okay, now my voltage supply will come here. Okay, so my voltage is say 10 volts, and my frequency is, let's say, 50 hertz. Okay, now I have to get one resistance which will act as my load resistance, and this resistance, this load will be measured between this point and this point. Okay, so I have my probes to see the signal. This one I have to measure between this and a reference here. So this again I will select the reference. Now let me just add a ground port here. Okay, and let me run. If we see the graph, okay, so again I've done the same mistake. Go back, and we are measuring here. Okay,
So reference means just like putting voltmeters and
exactly, ma'am. So
a
basically,
meter across.
exactly. That is what.
Okay,
Like
okay,
generally, if I see this probe now, this probe basically you see one terminal only. Okay,
yeah,
so by default, the measurement will happen at this point, which will be the
and
positive end. The negative end of this voltmeter will go to the ground.
ground. Yes.
Okay, so by default that is the connections. Okay, so if I
Okay,
put just like this, it will measure between this point and ground, but in our
okay.
case we have to measure across this, not
Yes,
between this point and ground, across this.
yes.
So
Across.
what we
Yes,
do,
yes,
we put a reference point here, and then
yes,
we go into setting, and here you
yes.
see we make it reference 1, not ground, reference 1, so
Okay.
that it knows that between this point it has to measure.
But we have to select only one point. The other
Yes,
we'll have to change it by going in and changing the setting from ground to reference.
yes, if double click here you see reference 1 and ground.
Yes,
So if
yes,
I make it ground, it will basically measure between this point and ground, which I
yes,
don't want in this case. I
yes.
want to measure between this point and this point here.
Okay,
Okay, I can put in multiple reference point and I can select any of those. Like if I want to measure between this point and let's say this point, so I'll put in a reference here and I can measure. This
okay.
reference is just like your negative of the voltmeter, where you
Voltmeter.
want to put
Oh,
it. Okay,
okay.
so it
Thank.
will give you optionality for that.
Okay, sir. Thank
Okay,
you. Thank
so now you see you again get your full wave rectifier. Okay, so now what we'll do, as ma'am said, we will try to add some capacitance to see if we somehow can increase or decrease these ripples. Okay, so let me just go to schematics, zoom it a little. Okay, now what I will do, I will take one capacitor. Okay, I will put it here. Let me rotate it. Okay, and this will be connected across this only. Okay, so right now this capacitor value is what? Let me just check. This is 1 micro. Okay, so let me just put it back. Okay, so this is 1 micro. Let me just decrease it to uh, let's say 10 or 1 nano. Okay, 1 nanofarad. So if I run this circuit now, you see you have the similar result, Now what I will do, I will try to increase this capacitor. You see the 1 second. Let me just do it like that. See, your wave, no result is happening. 1 second. You see, if I keep on increasing this, the ripples has gone a little low. Okay, so if I again see change it, decrease it, it will come back to the original. And if I keep on increasing it, as expected, the ripples are going down. Okay, so I can keep on increasing the capacitance further to even reduce it and make it almost a flat wave. Okay, so that way you understand, like right now it is 100 microfarad. So if I keep on again increasing it, you can see that it will keep on going flat. The ripples are decreasing. Okay, so this is the effect of a capacitor. It will act as your basically it will dampen the. So I hope this clears your doubt, ma'am. Any questions
Yes,
on
sir.
this? Do we have any questions on this?
Sir, while changing value of any component, we need not stop simulation.
No. Actually, that was a trigger. So trigger, we have to make it auto. If I make it single, it will take a screenshot here, and whenever I change the value, like it won't change anything
Yes.
because it took a screenshot at that time and it is showing me. But if I make it none, it will like keep on running here and there. So I will not see it properly. So that is why we make it auto. In auto, you don't have to stop. Like I can just increase it. You can see we don't have to stop or start again.
Right.
Okay, that I did because that time we were in a single trigger mode. So that was
Yeah.
a screenshot you were seeing. Okay.
Yeah. Thank you, sir.
Any further doubts?
Sir, excuse
Yeah,
me,
ma'am.
sir. Can you
Yes.
show that center tap? How will you connect that center tap resistor, sir?
In the previous one, ma'am.
Yes.
Okay, no, that I will show you, ma'am. First, you have any doubt on this, then let me know. Otherwise, I'll show you that one. Okay, so I hope there's no